Okay, so this will be our last lesson of this unit. We are working on something called a linear quadratic system. So let's just take this back to grade 10 for a second here. We have, in grade 10, early on in the course, we worked with solving what is called a linear system. And this is two or more lines. Usually we just did 2 lines on the same graph. Does anyone remember? So if I have 2 lines on the same graph, what would be like solving the system? What would I be looking for? Miguel? The point of intersection. Who remembers this word from grade 10? Point of intersection. Okay, good. So we had a couple options for solving a linear system. So if I have 2 lines on a graph, what are the different number of point of intersections I can have between 2 lines on the same graph? 1? Okay, so we can have just like a straightforward kind of example where we have 2 lines and they cross at some point of intersection, right? So this would be 1 point of intersection. I'm just going to say POI for point of intersection. What other scenarios could we have if we have 2 lines on the same graph? Is this the only possibility that I could have, that these lines have to cross? If they were. So if it's curved, then it's no longer a line. Okay, Cameron? 2 lines on top of each other. So suppose I have a line and then literally like the same line on top. How many points of intersection would these have? Chris? Infinite points of intersection. So every point is a point of intersection. Okay, there's one more scenario. See if we can think about it. Ella? And what scenario would that be? Okay, we have 2 parallel lines, and if they're parallel, that means they have the same slope and they will never cross. So 0 points of intersection, parallel. Okay, so now I'm going to tell you, we're going to have a quadratic, so a parabola, and a line on the same graph. I want you to chat with the people around you and see if you guys can figure out how many possible different scenarios there could be for how 1 line and 1 parabola could intersect if we put them on the same graph. Okay, I'm going to give you a couple seconds. See if you can draw out the scenarios as well. So what are all the different ones? Okay, feel free to chat with people around you, see what people are thinking. She's my like co-op student teacher person. So while you guys are thinking, this is Samantha Hawkins, yes. And she's my co-op student, so she's gonna actually be helping with this class. So she'll be here every day until maybe like a certain time later in the semester, depending on her hours. But she's here to help. She can also help you outside of class time potentially. So there she is in all her glory. She's taken this course. Are you taking calculus and vectors right now? Okay, so she's in calculus and vectors right now. So she's taken this course and she's taken advanced functions. She's really good at math. So, okay, so continue. Okay, so somebody give me one option here. What could we have if we have a line and a quadratic on the same graph? Clear? Okay, so we could have one point of intersection. So let's suppose we have some quadratic like this. And if we have a line that goes right down the middle, like so, I could have one point of intersection there. There's also kind of like a second scenario for one point of intersection, and that is what we call a tangent line. So if I have my quadratic, a tangent line is a line that sort of like skims the outside of your function, your quadratic, or it could be on another function as well, at like one single point. So we call this a tangent line. So this is also just like another scenario where we could have one point of intersection. So that's for both of these. And then this one's called a tangent line. Okay, I'm just saying that so that you guys have a visual of this, because we're going to talk about tangent lines at the end of this lesson. Okay, so we can have one point of intersection. What is another option that we could have? Maya. Okay, or it doesn't even necessarily have to be parallel. It could really just be any line, right? So this is probably like the most likely scenario, is that we would have like a line just cutting through our quadratic. So 2 points of intersection in this case. Okay, there's actually one more scenario. Does anyone have one on their page? Chris, what did you put? Okay, and how does that happen? Sure. So let's say maybe we have a quadratic opening down over here, and then I have like a line over here. Okay, or even if you're not sure, like those won't cross, you could have a parallel or like a horizontal line. So no points of intersection in this scenario. So that's possible as well. Did we miss any scenarios? Are there any other scenarios that we could have with a curve like this and a line? I think that's it. That covers everything. Okay, so how did we solve linear systems in grade 10? How did we solve all of these types of problems where we tried to find points of intersection? Does anyone remember? Some of you that had grade 10 math last semester might remember this. Okay, so one option is we could graph them. We can also do the same thing with like linear quadratic systems and observe where they're crossing. One of them was substitution. Does this ring a bell? And what's the second one? Elimination. Okay, so elimination is kind of difficult to do with a quadratic and a line. So we're actually going to use kind of like the substitution type method, kind of. So here's the steps. I'm going to just do the steps with you as we look at example number 1. So in the sense of substitution, remember that this just replaces y. So this is function notation. So this is like y equals and y equals. We actually sub this in for y in the other equation. So the first step is we just set the equations of the line and the quadratic equal to one another. Essentially, it's a method of substitution. Okay, so for part A, step number 1, set the line equal to the quadratic. Doesn't matter which one's on the left or which one's on the right. Okay, so that's step number 1, done. Also, why does it make sense if I'm trying to find a point of intersection? Why would it make sense that I set the equations equal to one another? What do the graphs have in common at the point of intersection? Marcus? So they have a y in common, and they also have more in common, Josh, which is like an xy coordinate, right? So when I find a point of intersection, I'm saying at that particular point, the line and the quadratic have equal x's and y's at that point. So see how we set them equal to one another? I'm trying to find where they share the same x and y. That's the idea. Okay, so second step, we're going to move all terms to one side and simplify. Usually I will just move the line because there's less to do. So move them all over to one side. I'll be left with 0 over here. Okay, and then second part of this says simplify. So gather your like terms. And this looks pretty familiar. This looks like something we're kind of used to seeing. Just looks like a regular quadratic now, right? So we know that it's not technically a regular quadratic. We know that it came from trying to find the intersection between a line and a parabola. But how do I solve for x if I have something that looks like a quadratic and it's set equal to 0? What are the different options? Claire? Okay, so one option could be quadratic formula. Chris? Or we can factor. Okay, so I have two options at this point. I can factor or I can use quadratic formula. At this step, I can actually use the discriminant. You guys remember b squared minus 4ac? We usually use it to predict roots. But since I'm doing a line and a quadratic together, I can use the discriminant to actually predict number of points of intersection at this point. So if we wanted to do like a quick prediction here, we could do, let me just move this over. We could do b squared minus 4ac, which in this case would be -9 minus 1, or sorry, times -9 squared minus 4 times 1 times -10. So we'd get 81 plus 40, so 121. Because this is positive, this tells me that we have 2 points of intersection between the line and the quadratic. Okay, usually, again, we use that to predict number of x-intercepts, but because we've done the line and the quadratic here, this is telling us about points of intersection. Okay, so we can factor. If we can't factor, then we go quadratic formula. So can we find any two things that multiply to -10 and add to -9? That would be the question. Sorry, Jacob, right? Okay. -10 and 1. Perfect. Easy factoring. So these go right into the brackets. X minus 10, x plus 1. How did I know that this was easy factoring and I didn't have to do the like splitting and method of decomposition where we do factoring by grouping? Chris? Right. So anytime x squared has a coefficient of 1, you can do the quick method. Okay, so what are my x's then? Maybe someone who hasn't answered yet. What would be the x values here? Abby? 10 and -1. We just take these in the brackets and switch the signs. Okay, so I now know the x's of the points of intersection. Every point has an xy coordinate. So I now need to know the y coordinates of the point of intersection. So we've done this. We are going to now take the x coordinates and we can plug them back into one of the two original equations. So it doesn't matter which one you choose. If you've gotten the x's right, they should give you out the same y's because they share the same xy coordinate when they cross. And then you find the y's. So I usually choose the line, but it's not a bad idea to plug it into both and make sure you get out the same y from both of them. But I'm going to evaluate f at 10 now. And I'm going to evaluate f at -1. Okay, so this is a good recap of function notation as well. How do I evaluate f at 10? What am I being asked to do there? Claire? Yes, so I'm going to use this one and we're going to sub in 10 for all the x's in the equation. So 20 minus 5. And f at 1, I'm going to sub in, or sorry, -1. I'm going to sub in -1 for the x's in the f at x equation. Okay, so can somebody tell me what are my final 2 points of intersection here? How would I write them as xy coordinates? Chris? Great. So when I plug in an x value into an equation, I get out a y value, right? So that's actually literally giving me the xy coordinate on that point. Okay, a good check that you can do is double check that when you plug these x's in the other equation, that they give you back the same y's that the line gave you. If they don't give you back the same y's, you found the wrong x's. Okay, so what did we just find? Let's take a look at what we actually found here. I'm going to go to Desmos and we'll look at this graphically for all of you lovely visual learners out there. Okay, so we had y equals x squared minus 7x minus 15. There's the quadratic. And then we had a line 2x minus 5. And let me just change the window here slightly. Let's go -10 to 15. Up to okay. So here's our line and here's our quadratic that we were looking at. So you can actually double check your work with graphing as well. So we literally just found 10, 15. This is one of the points where the line crosses the quadratic. And we found -1, -7, the other point where the line crosses the quadratic. Okay, so this one was the f at x function. This one was the w at x, the quadratic. Okay. So we're going to try a couple more here. The first part of this asks us how many times do they intersect the line and the quadratic, and then find the points of intersection. So this first part is asking us to find a prediction of how many points of intersection. I'm going to use this information over here with the discriminant to do that. So I will always complete steps number 1 and 2 first, and then that will allow me to make a prediction. So step number 1, what does step number 1 say to do? Sia? Okay. Set the equation of the line equal to the equation of the quadratic. Okay, what does step number 2 tell us to do? Pardon? Okay, so we have to move everything to one side. We'll combine like terms. So I'm going to move the 4x and the 10 over. Miguel, can you shut the back door for us there? Okay, and then as Blair said, we need to combine any like terms that we have. So I'm going to put the x's together and the constants. Okay, how many people out there love working with fractions? Oh, come on, guys. Nobody? All right, well, we like to make our lives a little bit easier, right? If we don't have to work with fractions, we don't really want to, right? That's what I'm getting from the fact that nobody put their hand up, that they don't like working with fractions. So we have a fraction in here. I can actually easily get rid of a fraction when I have an equation that's set equal to 0. Okay, I can't do this if there's like f at x equals. But if I have 0 equals or another number equals something to do with an equation and that equation has a fraction in it, I can actually easily get rid of this as long as I do to one side of the equation what I do to the other side, right? We know this, right? We must do to one side of the equation what we do to the other side. Okay, so how could I get rid of a division by 2? Technically, a multiplication of a half is like a division by 2. Kira? Okay, so I'm going to go through and I'm going to times every single term here by 2. And as long as I do it also to the left side and I do it to every term on the right-hand side, I should be allowed to do this. So I'm going to come through, we're multiplying everything by 2. And the reason why I'm doing this is that these will cancel and I'll just be left with x squared here. Could I have done this with the fraction still in there? Certainly. It would have required me to probably use quadratic formula because factoring something like this is maybe more of a challenge. This equation is equivalent to the one above. Okay, as far as the solutions, I should say. They're equivalent because they'll give me out the same x values. Okay, so here's my options. Oh, actually, we're going to do a prediction. So how many times do these intersect? So now I have a equals 1, b equals -4, and c equals 4. So we're going to do a little prediction with b squared minus 4ac. What do we get here? Here? Okay, so if b squared minus 4ac gives us 0, and I've combined a line and a parabola, this tells us we have one point of intersection. So Kira's right. Okay, so for part B, we want to solve this. So I have two options. I can try to factor if possible, or if I can't factor, then I will use quadratic formula. So the question is then, can we factor this or not? Are there any two things that multiply to +4 and add to -4? -2 and -2. So I'm going to put that right into the brackets, x minus 2, x minus 2. And technically we can write this as x minus 2 squared. So that's why we have one solution here, because there's only one value that x can be equal to. What's the value that x will equal? Josh? 2. Okay, and then I have the x of the point of intersection. What's the last part that I need? We need the y. So I've got x here. How do I get the y of the point of intersection? What should I do? Kira? Okay, so either here or here. I should get the same answer either way. So I'm going to plug it into the line. We'll evaluate g at 2. So 4 times 2 plus 10. and that will give us 18. So final point of intersection. Oh, is it? Sorry, I miswrote that. Okay, so -2 then. So final point of intersection. Clear? 2, -2. Awesome. Okay, if you can't factor at this point, guys, plug it into the quadratic formula, get your x's out, and then same thing, sub them back into one of the two original equations. We do not want to sub it into the one where we've set them equal to one another. We want to sub it into an original equation so that we can get the y coordinate on that graph. If you plug it in here, or if you plugged it in like here, you would just get 0 out from it. The reason for that is because you've already combined these into a single equation, and then it's changed the equation of what the original functions are. Matt? If you can do something in one step, like this was one step and we were able to find what x was, I would say you should probably be going that route, because if you're using quadratic formula, that's going to take a significant, maybe not significant, but it's going to take quite a bit longer than just finding the factoring thing, especially for like an easy quadratic. So I would say if ever you can factor, you go that route. If not, then quadratic formula will be your last resort. Okay, last one for today. This is a slightly different type of question. So if a line with a slope of 4 has one point of intersection with the quadratic function f at x equals half x squared plus 2x minus 8, what is the y-intercept of the line? Sometimes you will also see in these types of questions, it might tell you, instead of saying one point of intersection, it might tell you it's a tangent line. So if you see something that says tangent line, that's this scenario that we talked about here, where you have the line skimming the outside of your quadratic at one single point. So sometimes it will tell you, okay, it has one point of intersection, or sometimes it might use the word tangent line to indicate to you that that's one point of intersection. Okay, so look out for the word tangent line for these types of questions as well. I'm just going to put that as a note on here. Okay, and if it says tangent, it's the same thing as saying it has one point of intersection. All right, so I have the equation of the quadratic. I know the slope of the line. So if we were to call the line g at x, equation of a line, what's the equation of a line? So usually we say y equals, but Maya? Y equals mx plus b. So what is the slope part of that then? It is the m. So if I were to say like mx plus b, we know that m in this case is 4. And b is kind of a tough one to like use as a variable here, because we also have b squared minus 4ac in the discriminant part. So I'm going to choose a different variable for b to represent b. I'm just going to choose k for this for right now, and k will represent the y-intercept. Okay, so I'm going to follow the same steps as usual, the first 2 steps, which is I'm going to set the equation of the line equal to the equation of the quadratic, even though we don't have all the information. So I'm going to set the equation of the line equal to this quadratic. That's the first step. And then we're going to move everything over to one side. And then we'll gather like terms. Oh, sorry, this is plus. So yeah. And this is a constant term, meaning it doesn't have an x with it. So I'm going to gather these together. And this set right here, the -8 and the -k, that's going to represent the c value. I can't put them together because I don't know what k is yet, but that whole thing is the constant. It's like the c value. Okay, so follow steps 1 and 2 as usual. And then we're going to use the information about the number of points of intersection. So if I know something has 1 point of intersection, what information does that give me? Josh? Okay, so because we know this has 1 point of intersection, or if we knew it was a tangent line, we would also know it has 1 point of intersection. I know that b squared minus 4ac must be equal to 0 once these two equations are put together and simplified. So in this case up here, a is a half, b is -2, and c is like the combination of both of these. So we're going to write c as -8 minus k. And I'm going to plug them in here into b squared minus 4ac. So b squared minus 4ac will be equal to -2 squared minus 4 times a times c. And I guess we should say this equals 0. So we know that's equal to 0 because it's 1 point of intersection. And then I'm going to simplify here a little bit. What's half of 4? 2. So we can just write that as 2, right? -2. Okay, and then I'm going to bring this in, expand, simplify. We're trying to get k by itself so that we can solve this question. And if I have everything in the equation except for one variable, I should be able to solve for that variable, right? Can I solve for k here? Chris? Okay. Perfect. So I'm moving the 2k over to this left side here. It becomes -2k. And then we'll divide out -2 to get k by itself. So we're just isolating for k. And k equals -10. That's what I'm trying to find. That was my goal in the first place, is to find the y-intercept. So I just found that the y-intercept was -10. So we can write that as 0, -10. That's how we write a y-intercept, 0 for x and then the y. Okay, this is kind of like, it's actually this question above, but it gave us different pieces of information. Okay, so you actually don't even have to go through like a whole solving process after that. You're going to do the first 2 steps and then use the information about b squared minus 4ac. So if that's 1 point of intersection, we know it's 0, and then just solve using b squared minus 4ac. Any questions on this one? No, that's the y-intercept. That's what the question was asking. What is the y-intercept of the line? So that's like in y equals mx plus b, that's this, right? Which we let be k. So you wouldn't be able to unless you know all of the line information. So you could, but that's basically what we did up here, right? So if you wanted to then find the points of intersection, you could sub k into the equation of the line, and then you would just do this. These are the same equations that we actually just used below. So we've already done that for this question. Good question though. Any other questions? Okay, we'll take that as a no.